Hello, everybody, and welcome to the Designcenter Solid Edge simulation presentation. Today, we're going to talk about a few industry trends in simulation, an overview of the simulation tools and benefits of using them. We'll also look at the Solid Edge simulation products, as well as some use cases and examples. And then at the end, I want to talk about the Altair acquisition that Siemens made, which has added quite a few simulation capabilities into the Siemens portfolio. Starting with industry trends, the first is that the digital twin, which Neil had talked about earlier, is only growing. And in engineering and design, simulation is a key component of your digital twin. It is your digital version of your physical prototypes and physical testing. Um, so, and of course, with the data management tools and things like that, it can always be, tied in and managed um, in those environments. The next trend is that products are always getting more and more complex and requiring an integrated simulation solution. Meaning that it's pretty rare for a final product to be solely mechanical design. Most products these days have mechanical, electrical, um, and other domains that need to be simulated. So it's pretty often that a multi-physics or integrated physics simulation is required these days. And lastly, simulation is being used earlier and more frequently in the design process. Um, and this has multiple benefits that we'll discuss shortly. But what are simulation solutions? They are solutions used to recreate real-world systems, processes, and environments digitally. For engineering and design specifically, it's used to validate your designs virtually rather than using a physical prototype model. And so some of those benefits include a 29% reduction in development time. This is primarily because of using by having designer-led simulation and using simulation earlier, you're finding and addressing problems earlier on while they're still easier to resolve. It also using simulation and designer-led simulation also results in 21% fewer number of change orders after a product's release for a similar reason. Because the potential issues are identified and resolved earlier on in the design cycle, it results in fewer issues after the product release. And lastly, 27% reduction in the number of prototypes. This is just with using simulation. By using it in your design process, your initial prototypes will be more accurate and more likely to succeed, resulting in fewer prototypes required. So let's look at examples of the types of studies that we can do with solid edge simulation. We can analyze the stress in a loaded component or in a storage tank from hydrostatic pressure. We can look at a support frame for its factor of safety or how likely it is to buckle with solid edge. We can also look at things like the natural frequency of a pump and motor, and even analyze the motion of a conveyor system. And the products that are used for this are, these are the products in the Solid Edge portfolio. That is Simulation Standard, Simulation Advanced, and SimCenter FlowEFD for Solid Edge. So Solid Edge Simulation Standard offers linear static studies, which evaluate how a part or an assembly can respond under static loading conditions. It can also do linear buckling, which looks at how susceptible a component is to buckling when under compressive loads, typically used with longer, like skinnier, thinner components, like beams and railings. Normal modes identifies the natural frequencies and the shape of the mode shape of that structure with those frequencies. And finally, design optimization, which automates the process of refining design parameters. Um, Basically, it automates optimizing and iterating on your design by you plug in your design parameters, your design limits, the simulation um, parameters that you want to adjust, and it will automatically run multiple simulations to find the most optimal design. And we could take a look at an example of Solid Edge simulation standard here. So this is the subassembly that I'm doing my simulation on. Take a look at the simulation geometry. So this has been simplified a little bit. I'm mostly interested in the two C-channel beams. These are the top face of these bolts is our fixed point, and we have our force on the two sheet metal flanges that have been simplified into mid-surfaces. Now, I won't make everybody sit through the actual solve time here. These studies have already been set up and run. But I do want to explain the process used here, and I did one of the design optimization studies with this. So to start with, we have a force on the two bolt holes on either end of the beam with 20,000 newtons of force and a fixed constraint on the top face of these bolts. And when we ran that simulation, this is what our initial result had looked like. And so we had the maximum, like the total translation, the highest translation in the assembly was just over a millimeter. And we had a stress maximum around 298 megapascals. And so what I did is I created an optimization. And optimizations consist of a few different parameters. We can see that our target objective was 1 millimeter. Like I said, we had started above 1 millimeter, but because I've already run this one, I'm at 0.66. But I had set the target value to 1 millimeter. I had set a design limit so that the von Mises stress would be limited to 190 megapascals. Again, currently we're at 164.974 because I've already run this, but that is what I had set the limit to. I also declared two design variables, and these are variables in the part. So the linear 9 and linear 8 variables are variables of my parts, in particular the two C channels. Linear 8 is the length of the C channel, and linear 9 is the thickness of the C channel. And so I've given it a range of 2 to 6 millimeters and a range of 400 to 1,000 millimeters. I've also limited the number of iterations to 20. We didn't get that far. It found the solution before then. And then some convergence parameters that determine whether this determines whether it should keep simulating or if it's finished, basically. And so the way this works is it runs a simulation and the first study with the original design parameters, iteration 1, and then Anna takes a look at the results, changes the parameters, looks at iteration 2, and repeats this until you finish your design or the optimization study. And you get a little summary at the end that looks that in the form of this Excel sheet. It shows you your design objectives that I had set. At the beginning, I was just over 1 millimeter. We get our current von Mises stress, which was 297 before running it. We have our two design variables that I explained earlier. And then we get our optimization results. And then each column here is a different iteration. So we can see that the total translation was in the first was 1.005, then we had 0.884, 1.65, and so on. We can also see the different variables and what values it chose in each iteration. And then at the bottom here, we can see the design limits. Anything in red exceeds the limit that we had set. So iteration 4 was actually sufficient. It was under 1 millimeter translation and under our limit for von Mises stress, but it continued simulating because I think it could find a better one. And eventually, after the ninth, it determined that it wasn't going to find a better solution. And so we can actually look, in addition to the summary of the optimization, we can actually look at the results of each one. Primarily, we'll just look at 8 and 9 here. So we can look at view total translation. We are down to 0.66 millimeters. Stress, we are down to 185 megapascal. And if I go to iteration 9, we are at 0.657 millimeters and a 165 megapascals for our stress. And so that is what a design optimization study looks like. Again, this is available in Designcenter Solid Edge Simulation Standard. Next, I wanted to take a look at Solid Edge Simulation Advanced. So this has all the same capabilities that Simulation Standard has, but in addition, it includes steady state heat transfer, which computes the equilibrium temperature distribution in a steady state. It also looks at any thermal stresses, in the combined study. We can also do transient heat transfer, which can simulate the time-dependent temperatures and thermal or heat flux, depending so capturing thermal conditions with change over time. And then last, we can also do combined studies with steady state heat transfer and linear static simulations. So this evaluates both the thermal distribution, structural impact, and thermal expansion at the same time. So it's good to analyze your linear static or mechanical structural studies when the environment is going to be significantly hotter or colder than room temperature. And then, of course, the last one is harmonic resonance, which analyzes how well the design responds to vibration and loads, loads while under vibration. So identifying resonant behavior, amplification. This could be used in situations where you have rotating motors or anything else that causes vibration while under load. So we can take a quick look at an example of this using Solid Edge Simulation Advanced. This model is a little bit larger than the previous one. So this is the entire assembly, but I'm actually doing a study on just this box here. This has some electronic components in it, so we can switch to motor casing. So this is the box there, and we can hide the lid so that we can see a little better. So this is our motor encasing. We have the motor, I think, gearbox, and of course the casing, and then a PCB here. So this is a heat transfer study. Like I said, I've already run all these, so we won't have to wait for it. But to explain, the loads are a little bit different in a heat transfer study. So we have our convection, which is shown as a film coefficient, which is going to vary between different materials and components. But you can see here we've got 5 watts per square meter. And then we have our heat generation loads. So anything that is generating heat here. I believe we have a load of 25 watts on the motor and 10 in the, so 25 watts for the motor and then 10 watts for our PCB. And then our connectors are thermal connectors. So we can take a look at the results. Like I said, I had run these all ahead of time. And so this is the result of a heat transfer study. Again, this is static. And so the heat generation from the motor and PCB don't change. It is static. And this is where it would reach equilibrium with the coefficient we established with the convection coefficient. So the hottest temperature is around 84. We can use our max here. Yep, so 84, 86.4 degrees in, right at the end of the motor there, which makes sense. We can also see the temperature differences in various areas in the entire assembly. And we can use our probe command to get various, to get different readings. So on this side of the motor, we were at, 86. Maybe in the gearbox, we can take a look at 74.3 C. And then interestingly, we have some hotter and colder spots on the PCB. So, here is 33, whereas here is 58. So quite a bit of variation in different areas on the PCB, but this is what the result of a heat transfer study could look like. And then next is Designcenter Flow EFD for Solid Edge. So again, this is still integrated within Solid Edge. It is a computation fluid dynamics, and this actually uses, so it's using a different solver than the FEA studies. This allows you to do fluid flow, so you can analyze both turbulent and laminar flows under either static or dynamic conditions. So you can do transient studies or studies that have changing conditions. You can also do a heat transfer study, similar to what we had just shown, by simulating, heat conduction and convection, which would give you similar results to the heat to the study I had just shown. But you can also do a combined study, which is probably the most common use case, which couples fluid flow and thermal analysis at the same time into a single study, which shows how the fluid flows and how heat is exchanged and transferred between the fluids and solids. One of the most common use cases is in electronic cooling, although heat transfer designs are another common use case, like heat exchangers and things like that. All right, so this is the model that we're going to take a look at for our Designcenter Flow EFD for solid edge example. We're going to start by taking a look at the PCB here. Now this is a really good model. There's a tool that within FlowEFD that helps import your PCBs, but this is far too detailed for a CFD study. And so we're going to activate a simplified version. I believe the two capacitors are still in the study. They're just not being shown at the moment. In this study, we have heat sources from all of these components, as well as the 2 resistor chip here, which is at 4 watts. The others are much smaller. We have some polycarbonate materials declared there. And this is the computational domain. So this is the volume that the solver is accounting for. So we can take a look at the results of this study, and we can start by taking a look at this surface plot, which shows the temperatures of each component here. And so we can see that the 2 resistor chip, or the main chip on this PCB, is going to be the hottest location at 167 Fahrenheit. And then, of course, there's also, we can see some of the warmer areas around it. The other thing that SimCenter FlowEFD lets us see is the flow trajectories. So we get a good visual representation of how things are flowing, and both the temperatures, and then also you can do velocity of the air as well. In this example, this is just convection. There's no forced airflow. And we can take a look at we can actually animate the flow trajectories also to get a better idea of how things are moving. And so we can see that the air comes from below the board, up around, and goes up through the, away from the heat source of the board. But we can see that this is still not quite, it still isn't, quite cool enough. So we add a heat sink and see if that would help. So we can see the 2 capacitors now, but outside of the heat sink, everything else in this study is the same. So we have the polycarb capacitors and the aluminum heatsink here. And we can again load the results and take a look at our surface plot, which we can already see that the temperature of our primary chip and heatsink is significantly lower than in the previous study. We're around the 140 area, 140 degrees Fahrenheit, whereas before we were at 167. Again, we can show the flow trajectories and animate to see how things look. And we can see that the air still comes from below the board, but it goes up through the heat sink, and we can see that the temperature of the fluid or air is much hotter going through the heat sink, which is exactly what we want. The other thing that we can take a look at is the compare. So this compares the 2 different study results, and we can take a look at those side by side. So we can see on the right, we have the initial simulation with the 167 degree temperature, and then with the heat sink, we are down to somewhere around 140. So the second study I wanted to show with Flow EFD is with the entire motor casing. And so in this example, in the computational domain will be a little bit different. So we can take a look here. Again, things will be a little bit, pretty simplified. Um, there are a few active components that we can't see, and we can also show that the computation domain is just slightly bigger than the entire um, case. But the case is the primary domain, like inside the case. Um, what is declared is two environmental pressure boundaries. So these are outlets or inlets that just boundaries to environmental pressure. Um, and typically at room temperature. We also see that we have a few more solid materials that were declared: aluminum for the actual the case itself, some insulator material, polycarbonate on a few more material components, and then some typical plastic. Heat components, there's a few additional ones than the previous study. We have the motor itself plus all of the PCB components, and of course we still have the chips, two PCBs, and so those are the components in this study. So looking at the results, we can show the surface plots like we did before, and we can see that the heatsink and that primary chip are going to be the hottest areas. We get a lot more um, color bars in these simulations because there's a lot more going on here. And we can also, let's see, it's a little hard to see with the full case on, so we can turn that off so that we can see our flow trajectories. With the case on, you can't see them very well. And in this example, again, this is still natural convection. There's no forced airflow. And we can see that there's quite a few vortices inside the case, both above and also, well, I should say, both above and also below the PCB. And this means there's a lot of stagnant air that's not being replaced. And so the cooling of the board is not actually all that effective in this example. And so what we can do is see if adding a fan would help. So in this example, we've added a fan to this environmental pressure area. So this will have a forced airflow external outlet fan here. So this is pulling the air out of this device, which means this environmental pressure, it's going to pull air from here. And so I can go ahead and run this again, or not run, load. And so this is the surface plots with these results. The colors are the same, but the scales are a little bit different. I can show the comparison in a moment here. But I'm also going to turn off the casing again, just so things are easier to see. And then I can turn on our flow trajectories. And so we can see air coming in. It does still vortex over here, but we can see very clearly that the vortices above the board and also how much air is going through the board is significantly higher, and the actual temperature of that air is higher as well. and more heat is being pulled away from the PCB and heatsink. We can again turn on the flow trajectories. This really gives you a good idea of how things are moving and what these flow patterns look like. The static arrows do a good job, but this is always a better picture. We can see the air coming from the inlet. Some of it gets caught over on the right side, but that's not very consequential. A lot of the air is coming up to the PCB, being pulled through the heatsink, and of course, being pulled out of the the entire case by the fan. And so, like I had said, we can take a look at the comparison of the two results, or two studies. And this is a different style of comparison. We're comparing our goal plots. In the first simulation, the primary chip was at a temperature of 189.66 Fahrenheit. And in the second one with the fan, we are at 166.53. So a pretty significant difference between the two. And that's a much more effective method for cooling the device than just the natural convection. So that was the demonstration I wanted to show for SimCenter FlowEFD for Solid Edge. There's also several other modules available for FlowEFD. Like I had said, in the example I just showed, I used the electronics cooling basic modules, heat transfer, fluid flow, that's in the base. But there's also modules for more nuanced and, of course, the EDA bridge, which allows you to bring in your PCBs very accurately, and in other components for the electronics cooling center. There are also modules for HVAC. There's LEDs and lighting modules. There's advanced CFD, which includes the ability to simulate hypersonic flows and combustion. Hypersonic goes up to Mach 30, if I remember correctly. There's an electromagnetics module, which allows low frequency electromagnetic simulation. And then finally is extended design exploration, which is very similar to that design optimization feature I had shown for Solid Edge Simulation Standard. It's the same idea. You can input design parameters, design limits, simulation limits, and it will optimize your design by making various changes to those design parameters. So almost an identical concept, but this would allow you to do this with CFD parameters, both temperature and fluid flows and other goals. So there's many use cases for SimCenter FlowEFD. Of course, in aerospace and automotive, we're always looking at aerodynamics. Like I said, the most common one I typically see is with electronics for cooling. So things, heat sinks, PCBs, fans, etc. HVAC for analyzing, office comfort, ducting, ductwork, other components, and of course with oil and gas piping, pumps, heat exchangers, and that and those types of components and assemblies. Lastly, I wanted to mention the Altair acquisition that Siemens made recently. This really extended the simulation capabilities that Siemens has to offer. The simulation has always been very robust. With the Sim Center, there's been a lot that we have been capable of simulation, but with the Altair acquisition, there's even more that we're able to, capable of simulating a lot more like specific things, especially in manufacturing, that we're able to, run that Altair can run simulations for. If there's any specific questions on any of these capabilities, feel free to ask us, and we can get you in contact with the right people. And that concludes my presentation for Solid Edge simulation. Were there any other questions from anybody?